Yeah. What do you understand by the term datasheet? Have you seen datasheets of stuff of circuits earlier? What does a datasheet typically have?
Specifications of that device.
Specification of the device. What do you mean by the term specification, Animesh?
So all the data that a programmer or somebody who is working on it may need to make full use of that device.
So may
A
not
bit more.
necessarily be specification, but it is all the information. It may not be complete specification, that is, but it still has all the information so that someone can use it.
Yes.
So for a memory, what kind of information would you need to be able to use a memory?
Sir, it could be the operating voltage, the temperature, then total number of allowable read or writes, the capacity.
The right time. So the right time, the read time.
Yeah, the read and the write times, the typical minimum.
Okay. And
some also maybe like in the previous class we showed us that it could exist in different states. So maybe like that also.
Okay. Interesting.
Internet clock frequency.
Clock frequency, okay.
Endurance.
Endurance. SRAMs, unlimited endurance. Okay.
The
but yeah, flash ke liye you will need it, yes.
So capacitance values, the maybe.
Very interesting. We just talked about it, that the input capacitance has to be within a particular limit. Yes. And?
So size and PVT conditions.
Size and PVT conditions. Very good. And?
And like pen description and all.
दोबारा से बोलो साची.
The pen description can be the part of the.
Okay. Very good. So shall we look at one memory datasheet? Yeah. Someone was saying something.
Speed, sir.
Yeah. Frequency we talked about. Yeah. Speed. We talked about read speed, write speed. Yes. एक part अभी आप भूल गए. What do we talk about when we talk of circuits? Area. Someone said size. Yeah. Area. Area is very important. Yes. And?
Sir, figure of merit.
What do you mean by figure of merit?
Sir, noise margin values and.
What will a user do with that? But yeah, okay. Let us assume that for somewhere you will need SNR for a data sheet of a PLL, for example, or a ADC, you will need SNR also. Yes, definitely.
Version, sir.
Version, okay. That is also important because as the version changes, timings and functionality may change. Yes.
Okay. Capacity.
Capacity, yes. Okay.
Leakage.
Power की terms में अब आ गए आप. Leakage, yes. And?
The power consumption.
Power consumption, when?
It's in idle state or in like operating different.
Yeah, in all the various states, what is the kind of power consumption?
Yeah, and leakage also in the same.
So it should definitely talk about all the three at least. PPA, performance, power, and area. All three should be clearly evident in the data sheet. Okay, what else?
Supply voltage for operating this. Might be some load, how much load it can.
Okay, the load range and everything, yes.
The timing constraints. Timing constraints.
Timing constraints, yes. We talked about frequency and speed and everything, yes.
Technology node, which nanometer, 65 or 90?
Yes, which technology it is. So you should be looking at the right data sheet when you are designing something into your circuit. Yes. Very good. So shall we look at one data sheet? You've almost covered all of it, what we need to put there. So is it okay if we move to a data sheet now?
Yes, sir.
Okay. So this is a data sheet. This is from ST Microelectronics. They have very kindly allowed us to use it and for your purposes. So look at it. You talked about version, which version it is. It also talks about which date was it generated. The version may be 3.2 and the date. So that how old is this version? And you see, it also talks about something. 512 words, 774 bits. It says synchronous single port SRAM with 8 multiplexer inputs. So 512 cross 74 M8. And then there is also a prefix CMOS M55, which could be the term that they use for technology. ST, that ST is the one that developed. ST is the vendor for this particular memory. SPHD, single port, high density. LL typically could stand for low leakage, and so on. So there's the first page, you need to have at least this kind of information there. Then you see, now, okay, so this is a memory data sheet in PDF format. But typically memory data sheet, when you will generate a memory instance, memory data sheet may be available in either PDF or HTML or text, or maybe all these kinds of formats. It will be made available to you when you purchase a memory from a vendor. It could be in any format, but what we are interested to look at over here is what are the typical details that are given in a data sheet, so that when we ourselves either become memory designers or want to become system architects, whatever, and we want to use memories, what are the important things that we need to look at? Someone having done this course, MDT, should know at least this much, how to read a memory data sheet. Am I right? This is one of the most fundamental things that someone who has done this course should know. So we have this table of contents which talks about symbol and pin description. See, you never talked about pins. It also has pin description as to what kind of pins exist in the particular memory. And then we already talked about timing characteristics, power characteristics, leakage characteristics. So let's look at what it means one by one. So let us say we want to look at cell characteristics. So it says the number of words is 512, number of bits per word is 74. Number of multiplexer inputs is 8. What is this mux? We did not talk about it in the last class also. But what is this mux? What do you understand by mux? Anyone?
Sir, you said for selection of column we use it.
For selection of column we use it, but I have a 512 cross 74 memory. So where does column come in? I have 74 bits. I want to read all the 74 bits. You simply accepted, but I said you did not question me.
We're reading one bit at a time, right? Not the complete word.
Why? You're not talking about a serial bus. The processor would need all the 64 or 74 bits from any location now. When you look at a processor, you say load address 5. So does it load only one bit of address 5? No, it loads all the 64 bits of address 5. No?
Sir, I asked same doubt last class. You said we will get that
Yeah, that is what I want to enter into. I'm just trying to see if you have the answer already or not.
Sir, to maintain the aspect ratio.
Maintain the aspect ratio. What do you mean by aspect ratio, Nikhil?
Number of word line in column and rows. We want to maintain number of word lines.
Yeah, why do we want to do that? You're right.
So
you're not wrong. I'm just asking
that
why.
The delay reduces. Like if column is very high, so the bit lines will be large.
Sir, we want to make it a squarish memory.
You want to make it a squarish memory. Okay, why is it not a square memory, Abhi?
So वर्ड्स और बिट्स ज्यादा, वर्ड्स ज्यादा है, बिट्स कम है, तो रोज और कॉलम्स, या तो रोज बढ़ जाएंगे, कॉलम्स बढ़ जाएंगे.
So what we are seeing is that the number of words is much more than the number of bits, huh?
Sure.
Okay.
Sir, the number of bits which 74 is, that is the number of bit cells we have in the array, right? 74 bit cells we have in the array.
Yeah, 74 bits per word we have. Okay, so let me switch over to the whiteboard. Are you able to see my whiteboard?
Yes, sir.
Okay. So let us say we have this. Let us forget this 512 cross 74 for a moment. Let us say I just want to make a 64 cross 2 memory. I can want it. I can want a 64 cross 2 memory.
Yes, sir.
So what will I have? I will have a very tall memory where there are 2 bits per word and there are 64 such rows. And this is 2. Am I right? So what is the aspect ratio of this? 1:32. So agar mera have you seen pictographs of chips, ICs somewhere? Do you realize they are usually shown to be or designed to be squarish?
Yes, sir.
Now what I am saying is, in this squarish chip, make a memory which is aspect ratio 1:32. What would happen? Overall, this doesn't work now. If the chip is squarish, you would want something like a ratio which is manageable. Additionally, let us look as a memory designer only. Over here, my bit line has a capacitance of 64 rows. My word line has a capacitance of 2 columns. So the way the RC is distributed across word line and bit line is very skewed. In fact, my bit cell is very small. For write driver, I could actually have a big buffer. I can actually design a big buffer, but bit cell is bound to be very small because area is diamond in memories. So somewhere I could have a big driver. I do not have a capacitance to drive. But where I had a very small driver, the bit cell was very small, I have to drive this long capacitance of bit line there. So what would you want to do? You would say somehow, yeah, I can drive the word line faster. You say I can drive the word line faster, but please reduce bit line capacitance. So what do? You say, okay, let me fold the memory. So how do you fold the memory? You say, I will put 2 words per row. Instead of just 1 word per row, I will put 2 words per row. So what happens now if there are 2 words per row? How many rows do I have now?
32.
Half 32.
And how many columns do I have?
4.
How has my aspect ratio changed?
1:8.
And what do I now need to do? At a different level, what I now need to do is I just need to put a multiplexer here. है ना? That there will be 2 bits that would come. Of these 2 bits, depending on my address, one of the bits should go out. Are you able to see this? So that is why this is called as mux. Then let us say, oh, 1/1:8 is also a bad ratio. Can I do still better? So what do?
Sir, more folding.
I do, let us say, 1 more folding. I go for an additional fold and I say, okay, fold it once more. So now how many words do I have per per row?
4.
4 words per row. How many columns?
16.
Hmm?
No, 8.
8. And how many rows?
16.
16.
My aspect ratio has become 1:2. More manageable? Bitline capacitance has reduced by 1/4. Wordline capacitance has increased to 4 times. And we call this as mux 4. Because there are 4 words per row. So what do you need to do? You need to bring 4 inputs, of which 1 would go out. Are you able to see this?
So I'm not able to understand the mux operation.
Okay, so now when you not understood the mux operation, very good. Thanks for asking. So let us say now I selected this particular word line. How many bits will be written into?
8 bits are there in a word
But
line.
I have only one address with me. I wanted to write only on one word. So which word will I write into?
Which word?
So I'm doing a write operation.
Yes,
When I
sir.
select the word line, 4 words get selected.
Yes, sir.
But I wanted to write only on one word.
So that will have to tell them na ki write in that.
Where do we tell them? How do we tell them?
Through that mux.
Yeah, that is why you need the mux.
Okay. Okay. Yes, sir.
You got it?
Yes, sir. Yes, sir.
So
yes.
So here only, like each word would have multiple bits, right? So for example, if I want to write on the like four word, last word, like the 4th word. So each of these lines that you have said that it's mux 4, you have 4 lines. So each of these lines will be corresponding to all the 8 bits of that particular word.
No.
I mean, all the bits of that. So because in each word we have multiple
So in
bits,
fact,
right?
there will be 2 muxes here. There will be another mux. This will be for the second bit.
Okay. So if we have, say, in a word, we have 8 bits, so there will be 8 muxes here.
Yes.
And the number of mux will be depend on how many words in a particular row. And okay.
Yes. That is the mux size.
Okay. This 4
Sir.
represents that. How many mux in how many words for a particular row.
Yes.
Okay.
Sir.
Yes.
So the data sheet that you have shown us, that is 74 bits. But that the number of muxes were 8. Then what's the case in that? Like,
so over here there are 2 bits, but the mux is 4.
2 bits. So I'm not getting it. Like,
mux 4 means how many inputs per mux?
Yes, sir. Yes, sir. Yeah.
And how many muxes? The number of bits.
Yes, sir. So here we have 8 bits. That's why we have 8
No.
muxes.
Here we have this. This is a 64x2 memory instance.
Okay. So we have 128 bits.
Total, yes.
Yeah. In a word line, we have 8 bits, like after the folding it twice.
Yes. After folding, we have 8 bits because mux 4 into 2 bits per word.
Yes, sir. Okay. So can you relate this with that 512 is to 74?
Yeah, that's good. Let's do that. I think that will make it much easier for all of you. Let us say there is this memory which has 512 words and 74 bits. So now in that particular memory, they said we have mux 8. What that means is, first you do one folding, this becomes mux 2. Then you do next folding, this becomes mux 4. Then you do one more folding. And it would become mux 8. So how many rows would you have finally? 5 and 2 by 8. 64.
Yes. Yes, sir.
How many columns would you have? 74 into 8. What is that?
592.
596. So this memory would have 596 columns and 64 rows. Mux is 8. Columns is equal to 596. Rows is equal to 64. Words was already given as 5 and 2. Bits was 74. Is this clear?
मतलब sir, word per row is 512 divided by 8.
Words per row is 8.
Okay.
Sir, here still that this not aspect ratio is not equal to 1, or it will not make it a square.
Yeah, so that is why I asked you, why do we only want to limit it to aspect ratio?
So, but we are using this mux, we are using more area for implementing the multiplexer also.
See, you do not yet have the sense of area in this system yet. I have not told you what is the X and Y of the memory cell. I have not told you what is the area consumed in the row decoder. I have not told you what is the area consumed in the IO region. So you cannot, just by looking at my cartoon, tell me that, okay, the area is more or less. You can't. Array area will anyway remain constant because the number of bit cells is constant. But overall memory area, how it will change, we can't say that just yet with the kind of information we have till now. Are you able to see this?
Yes.
Sir, so in this, there will be 8 mux and each mux will have 596 kind of lines coming to it.
No.
Sir, here we'll be having 74 mux and each of which is 8. Each of mux will take 8.
Because there are 74 bits, I have 74 outputs to give. So there will be 74 muxes. Each mux will accept 8 inputs because each row has 8 words.
Yes, sir.
Is this clear? See, multiplexer is an important concept. You need to understand it well. Because if this is clear, I will go to the next step, which is called as bit interleaving.
So there will be 74 muxes and each mux will be 8:1.
Yes.
Okay. Okay.
Sir, here if we introduce mux, then the select lines for the mux will be based upon the address information that we give to the memory, and also the decoder size also might change based upon the folding which we do.
Yeah, obviously, because earlier you had to decode 512 words, so you needed 9 bits. Now you only need to decode 64, so you need only how many bits?
6.
6 bits. But you need 3 bits to decode the column address.
Yes.
So you still need all the 9 bits because your memory is 5 and 2 words.
Yes, sir.
But 6 bits for row decoding, 3 bits for column decoding.
Yes, sir.
Anything else?
So can you repeat about the capacitances you were saying about the word line and the bit line? How are they dependent if we like hold the memory and if the memory remains constant?
Yeah, you tell me when there was no mux or when the mux was 1.
Okay.
Let us say per row, the bit line has a capacitance of CR. So what was the bit line capacitance?
So number of bits into CR.
Yeah, so to give me the capacitance number. How many rows are there if there is mux 1?
So in this 512. So 74.
Mux 1, number of rows.
Number of rows. Okay, rows 5 and 2.
5 and 2. So then the capacitance was
512 CR.
512 CR.
Okay.
What happens when the mux is 8?
64 CR.
64.
Okay. When we like fold it.
Yeah. है ना?
Okay. Yeah, it's
It is only this long, otherwise it was this long.
Yeah, yes.
Now let us say per column, the wordline capacitance is CC. So initially, mux 1 mein, what was the capacitance of the word line?
74 cc.
74 cc. What is the word line capacitance later?
596.
596 cc. So what have I done? I have reduced bit line capacitance and I have increased word line capacitance.
Word line capacitance, right? Okay.
Does this match with what I wanted to do earlier? I said I could actually have a bigger driver for word line. है ना? You remember I had said that word line driver could be much bigger than because bit cell is small, but word line I can have a bigger driver. That is what I have achieved now.
Yes, sir.
Yes, sir.
Is this part clear now?
Yes, sir. Yes.
So I have one thing to ask. Like in the data sheet, it was given 512 words and 74 bits. So the memory is actually designed like 512 rows and 74 bits in each row. Or with that 8 marks information, we can deduce that the memory is designed like this folded one.
So the mux in the data sheet was given to be 8, na?
Yes, sir.
So what would it mean?
कि फोल्ड किया है मतलब एक्चुअल में ऐसी ही डिजाइन है मेमोरी
64 क्रॉस 596 की तरह डिजाइन है.
ओके
है ना?
सर 596 कैसे आ रहा है? 74 into 8 कर रहे हैं ना हम. तो 592 होना चाहिए उसमें.
हाँ, सॉरी 592. यस, सॉरी.
ठीक, थैंक यू.
सर कंटिन्यू द फैजल क्वेश्चन. डायरेक्टली ऐसा क्यों नहीं दिया है कि 64 एंड 592?
डायरेक्टली ऐसा क्यों नहीं लिया है?
मतलब डेटा शीट में ऐसा डायरेक्टली ऐसे क्यों नहीं है कि 64 इज द वर्ड लाइन?
क्योंकि द प्रोसेसर वांटेड टू हैव 74 बिट्स पर वर्ड. Processor wanted 512 words to be addressed.
Yes, sir.
So I had to have 9 address bits, na?
Yes.
If I would say the memory is 64 cross 592, then the memory would become 64 words and 592 bits per word. That was not what the processor needed.
Yes, sir.
So here the mux concept comes in because we want to improve the performance, right?
We want to improve the aspect ratio. We want to improve the performance. We want to change the power, whatever.
So, but like to me, it seems that it is coming at a very big area penalty because it does it. I mean, right in that because mux.
So I just told you that you do not know what is the area of the row decoder or what is the area of the IO. How can you estimate the area penalty here right away?
Okay. Yeah, right. So. Okay.
Can you? Array area would remain same. Can all of you agree on that? Because the number of bit cells have not changed.
Yes, sir.
Yes, sir. Yes.
So now, whether it is an area penalty or an area gain, you cannot know unless you know the row decoder area and unless you know the IO area.
Yes, sir.
Or can you imagine?
No, sir, not right now.
So cannot deduce that. Let us not jump into conclusions. We do not have the required information yet. I'm just making some cartoons for you.
Yeah. So and aspect ratio we want to be squarish because it like fits into that kind of like packages.
Yes.
Squarish. Okay.
So even same number of rows and same number of columns does not mean aspect ratio is squarish. By the way, I have not told you about the aspect ratio of the memory cell in itself in the first place. Have I told you? Nahi na? So this logical aspect ratio that we were talking about, that does not really mean the physical aspect ratio is also a square. What if the bit cell is much taller than it is wider? Or vice
Okay.
versa.
Right, sir.
So again, don't read too much into the cartoons that we are making here. I would try to keep it as representative as possible, but even then, don't read too much into it. Shivam?
Sir, sorry, sir. I must not understand the point. Like you said, bigger. We need bigger driver for word lines, sir.
We
Why
can
do
make
we
bigger
need?
driver for word lines because they are not a part of the memory cell.
So they are external. That's why we need. We can make
We
them
can
bigger.
make bigger. Yes.
Yes, sir. Thank you, sir.